Okay, in this podcast, we're going to take a look at how to calculate the change in enthalpy based on bond energies. Now, this is in Chapter 8 of your book, not in Chapter 5, which we've been working in. So make sure if you're using the book predominantly, that you look at Chapter 8, because this is probably the most important way that the College Board wants you to be able to do change in enthalpies. They are pushing it in the new curriculum to use the whole concept of bond energies to figure out enthalpy. So it's critical that you know how to do this. If you get nothing else out of the course this year, I'm hoping that one thing becomes really clear, and that is if you are breaking a bond, you must provide energy to do that. It is an endothermic process. You need to not just graze the bond, but you need to smack it, right? It has to have sufficient energy to break a bond. You must provide energy because there are nuclei here attracted to electrons here, and you are breaking that Coulombic attraction. There are nuclei here and electrons here. You are breaking that Coulombic attraction. Okay. And the second thing, of course, is that when you form a bond, you are releasing energy. You've got to release energy when you form a bond, because that's why bonds form, right? So remember, if I'm talking about an ionic bond, I'm talking about losing electrons or gaining electrons in order to get a full octet. If I am forming a covalent bond, I am doing that. I'm sharing electrons in order to get a full octet. So it's all about when the bonding is to become more stable. And more stable means lower in energy. Energy goes down. Now, one of the things that is often I've seen on most versions of the test, of the AP test, is this diagram that's on the first page of your packet. It looks something like this, right? And what that is showing, this axis is the bond length, and this is the energy, potential energy. And what it's showing is if I have two atoms and they are far enough apart, there is not going to be any attraction because the nuclei can't feel the attraction for the electrons. But as those atoms get closer, that attraction comes into effect, right? And once they get some attraction, they pull each other closer together until they hit this sweet spot where the potential energy is minimized, right? If they get too close, now I have the nuclei of one and the nuclei of the other repelling each other, and the repulsive force is greater. So bonds form at this length where the potential energy is minimized. And if you remember looking at that animation in the first podcast, that's where you saw all the shaking and stuff, right? That's to indicate that their energy is being released. Okay? So potential energy is released when bonds form. So if I want to determine my change in enthalpy based on the bond energies, what I need to look at is what does it take to break the bonds, which is always going to be positive because it's endothermic, takes energy. And I'm going to subtract from that the energy that gets released when the bond is formed. Always going to be negative, this release in potential energy. Okay? So the change in enthalpy, ignore again these boxes, it's the bond energies, the energies to break the bonds, which is always going to be positive, minus the energies, it's always a minus, right? Energies when the bonds are formed. Okay, so it's the energies of the reactants bonds minus the energy of the products bonds, right? When I'm producing them. Be really careful. It's not unusual for me to see students make a mistake on enthalpy changes associated with bond energies, because this is the opposite of what we do with Hess's law. Remember, Hess's law is the enthalpy of the products minus the enthalpy of the reactants. Okay? This is going to be the opposite. It's going to be the enthalpy of the reactants minus the enthalpy of the products in terms of the bond energies. So let's take a look at how we do this. It's easy as long as you keep in your head the common sense associated with breaking a bond. It's positive energy. I'm going to subtract the energy that gets released when I make the bond. Okay, so the first thing you need to do is get clear about what you're doing. Now, there's two ways to do this. One is now this is a pretty simple one, but you can either just look at what bonds have to be broken and what bonds have to be formed, or what I think is easier, typically, is you look at all of the bonds associated with your reactant and all of the bonds associated with your products, and it's the energy associated with the reactants minus the energy associated with the product. Okay, so let's take a look at what we have here. So we have H, right? We're breaking this bond. We have an F, we're breaking this bond. And we are making two HFs. So energy release when these bonds are formed. So the change in enthalpy associated with this reaction as it is written is going to be the bond energy of the products minus the bond energy of the reactants. So in this case, the bond energy of the product, so it's going to be the H bond plus the F bond minus the energy associated with two HF bonds. Okay. So the energy associated with the HH bond is 432 kilojoules, and the energy associated with the FF is 154 kilojoules. And I'm going to subtract from that the energy associated with the HF bond, which is 565 kilojoules. And if I add those all together, I need to multiply this one by 2, right? Because I'm making 2 of those because it's as written, right? So if I do that, I'm going to end up with negative 544 kilojoules per mole. It's that easy. Okay, I'm going to stop there.